All right, 10.1, limits and motion. The tangent problem.
Seems like a weird movie.
Well, these do get to be more like word problems, so.
No.
Not bad word problems, though. Like, they're not, like, awful or anything. They're not. You'll see in a second. All right, so our first definition is for average velocity. The change in position divided by the change in time. So an example, an automobile, I'm just going to say a car because, easier, travels 120 miles in 2 hours and 30 minutes. What is its average velocity over the entire 2.5 hour interval?
I gotta write it down.
I'm going to go back and put the formula for average velocity here, like written out in symbols rather than just in words.
My hand already hurts. I don't know how I'm gonna get through this.
I'm not even a third of the way through the first page.
I know, like, what?
However, this is also for anybody taking physics and intro to physics,
Oh,
this particular example.
well, that's good.
You know, I was gonna change my major, but then I looked at like the course requirements, and it was like up to Calc 3 and up to Physics 2, and I was like, no, I think I'll stay in mine. I think this is fine.
I'm never gonna escape calculus.
Right.
There's some places where I can choose like a biology thing and I can escape physics, but you just can't escape calculus.
I tried to skip physics and just take biology, and they told me, that's funny. You need the one that has math. Okay.
Yeah.
It's like any other options, anything but physics. Because I was very adamant that I was not going to teach physics, and then, I came here, so it was fine.
My mom said she loved physics. She got to build like a little bowling alley apparently, and like it had like little motors, like lights, and it worked. And I was like, how did you even do that? She was like, I don't know.
It's fascinating to me, but I don't like doing it, if that makes sense. Like,
Yeah.
I enjoy understanding, like, how the roller coasters at Busch Gardens work. Love that part of it. But it also makes it so once you've learned a lot of that, you don't ride roller coasters the same way ever again. Because your mind is thinking, what is happening as I go up? What is happening when I get to the top? What's happening when I go down? Why does it feel like this? Like,
That's funny.
And car.
it's like literally after we ride like a new roller coaster or something, my dad and I are like literally talking about the physics of the ride.
That's funny.
So it's like, it's just very different, but it's fine. That stuff fascinates me. The rest of it, not so much.
Maybe we could go to Spartan.
I'm all about that. I also would like to do the physics Olympics, but
How many people do you think have?
just 4.
I don't think we want to record physics.
All right, so average velocity is equal to delta S, which is the change in position, over delta T, which is the change in time. So change in position is 120 miles. Change in time is 2.5 hours. And so when you divide that, that's equal to 48 miles per hour. All right, next definition is instantaneous velocity, or well, it's not exactly going to be a definition, but it's the next topic. The definition will come up in a second, more or less. So we're going to look at a velocity question. So basically, I'm going to pop over in the book to where it is. Basically, this whole idea came up with Galileo doing an experiment with gravity by rolling a ball down an inclined plane and recording its approximate velocity as a function of elapsed time. And so this velocity question is like a possible thought about what was he looking at when he did it, kind of. So a ball rolls a distance of 16 feet in 4 seconds. What is the instantaneous velocity of the ball at a moment of time three seconds after it starts to roll? So instantaneous velocity is velocity at a specific instance. So at 3 seconds, what is the velocity? So the way we think about this is to think about the ball being frozen at a moment. Okay, now if the ball is frozen, what does that mean the velocity is? 0. So that would imply velocity is 0. So if we were going to do average velocity for this, we would have, again, it's the change in position over the change in time. So it changed 16 feet in 4 seconds, which gives us 4 feet per second would be our average velocity. But because our instantaneous velocity is at a specific time, and we're saying to imagine that it is frozen in time, then we have, if we were to do the average velocity or to calculate it the same way, the change in position if it's frozen is 0. The change in time is also 0 because it's at a specific moment. So dividing by 0 means this would be undefined, which is a problem. So we would have to approximate it. And so kind of hold that thought about instantaneous velocity because we're going to talk about how we're going to have to go about solving that with a definition.
Are you making up these notes as you go? Because I know sometimes
I am not.
well, I was just asking because I know on some sections that you've covered you already have
Oh, yeah, no, I did this yesterday. I went through because I was like, I need to make sure we cover everything. Plus, you have to think about it. I have now not taught calculus in a year,
Yeah.
so I kind of need to
Little refresher.
review myself anyways, so. And honestly, this book does a really good job of explaining this stuff. Almost better than the calculus book itself, so I'm like. But this is also a couple sections of calculus in one, so if that makes you feel any better.
Okay.
Go a little bit
It's so
deeper.
long.
Like, let's just teach a whole chapter.
So the definition of a limit at A. So this is where all of those, what happens as X goes to whatever, what it kind of is coming back into play. They're a major topic of calculus. We've only done stuff briefly with like in behavior and limits. It's getting blurry. Let me fix it. So when we write something like the limit as X approaches A of f of X is equal to, and we write it as capital L. And so this means, or we mean that f of X gets arbitrarily close to L as X gets arbitrarily close but not equal to A. So instead of now, like, as X goes to infinity, what's happening to Y, we're looking at as X goes to a number, what's happening to the function. So going back to our instantaneous velocity, we are going to use limits to solve that. And that's going to avoid the division by 0. So, an example, use limits to avoid division by 0. So we're kind of looking at a similar problem, just without numbers, to the other problem that we were looking at. So we have a ball rolls down a ramp so that its distance distance S from the top of the ramp after t seconds is exactly t squared feet. What is the instantaneous velocity after 3 seconds? So basically, we are going to see what happens to the quotient by treating it as a limit of average velocity on the interval And notice it's closed brackets on this interval because we are including, so 3 to t as t approaches 3. I'm going to let y'all get this because this next thing is where it really gets into the limit stuff, so let y'all catch up.
The Big Mac dipping sauce. Mac sauce dipping sauce. Like, I don't know why.
Good. Everybody got it? Okay, so what we're going to do is we're going to be taking the limit as t approaches 3 of delta s over delta t. So we're taking the limit of the function with respect to average velocity. So this is equal to the limit as t approaches 3 of t squared minus 3 squared, because that's the change in position, over t minus 3. Now, does anybody recognize what we have on top?
It's a difference in squares.
Yep. So I can rewrite this as the limit as t approaches 3 of t plus 3 times t minus 3 over t minus 3. Now, does anybody see what we can do?
Absolutely. I crossed that minus 3 out.
Yep. Bless you. Cross those out, and that leaves you with the limit as t approaches 3 of t plus 3. And when it says the limit as t approaches 3, we're approximating, so we're plugging that number in. Okay, so if I plug in 3 for t, then I get 6. So my answer would be 6. And this is the instantaneous velocity.
Okay.
Remember, it's technically just an approximation of what is it at that time. So we're saying as it gets close to 3, so we're using 3. So we know it's not going to be exactly that, but it's close. So that's the number we're going to use for it. All right, another example. Finding the slope of a tangent line. So use limits to find the slope of the tangent line to the graph of s is equal to t squared at the point 1, 1. So we're doing the same thing, plugging it in the same way, and this will give us the slope of the tangent line to our parabola, basically. So we have the limit now as t approaches 1 of delta s over delta t, which is the limit as t approaches 1 of t squared minus 1 squared over t minus 1. And so what do I have on top? So I have the limit as t approaches 1 of t plus 1 times t minus 1 over t minus 1. Things cancel. Because if this doesn't cancel, I still have 1 minus 1 on the bottom, which is 0, which I can't have. So something's going to have to cancel or at least reduce down when we're finding limits like this. So then we're left with the limit as t approaches 1 of t plus 1. So if we plug in 1 for t, that would be equal to 2. And that would be the slope of the tangent line.
Just finish writing down the part.
So I'm going to write one of those little random note things here. The method for solving a tangent line problem can be used to solve instantaneous velocity problems. Okay, good. I was getting a little worried there. I'll let y'all catch up. So basically all that note means is what we just found in the last two examples is that you can use the same method to solve both.
Okay. Yeah, so I was saying, but like, where is it?
Good. Everybody? Okay. Fantastic. All right, next is average rate of change.
Have we gone through a page yet?
Yeah, we've gotten through 2. We're at the bottom of page 3. Now, when you heard rate of change in Algebra 2, what did I tell you to think about?
I have no idea. I'm so sorry.
Because now I got like the rate of reaction for chemistry. I don't know.
I'm so sorry. I do not even.
How about slope?
Oh.
Maybe something about that.
Okay, so if
I know what it is. Yeah.
y is equal to f of x, then, now obviously this is slightly different because it's average rate of change, but then the average rate of change of y, all right, now I'm going to write this. WRT means with respect to, because I don't want to write that out every time. So the average rate of change of y with respect to x on the interval, or the closed interval a to b, is delta y over delta x. So hopefully that's where you see the slope formula. Just written a little differently, is equal to f of b minus f of a, so it's y2 minus y1, over b minus a. Geometrically, this is the slope, look at that, of the secant line through a f of a, through that point, and through the point b f of b. Which is where I said y2 minus y1 over x2 minus x1. We're on to page 4, everyone.
What does that mean geometrically? This is the slope of the secant line.
So, like, if you were to, like, draw it out, that gives you the slope. Those points would be on the secant line. Okay, the next thing, well, this method of doing it is not my favorite, but this topic is one of my favorite things to do in calculus, of derivatives. So, the first one is a derivative at a point. Now, I'm going to teach you I guess I should say the foolproof way of doing it today. Later, I'll teach you the shortcut. Because the shortcut doesn't always work, because there's a lot of rules. So the derivative at a point, so the derivative, like this is like chapter 3 of the calculus book, in case you wanted to know. The derivative of the function, but you'll have like the best foundation going into calculus, whether you're here or somewhere else taking it, of any of my classes.
Yeah.
So the derivative of the function f at x is equal to a, denoted by f prime of a, in red, well, okay. It's f apostrophe a, but it is read as f prime of a. Is f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a, provided the limit exists.
That makes sense.
because sometimes the limits don't exist. So for this one, geometrically, this is the slope of the tangent line through a f of a. Now, it's going to be the same heading, but I'm writing it again because it's another topic, like, in it. But for the derivative at a point, this method is going to be easier for computing and what we use more often. So the derivative of the function f at x is equal to a, denoted by f prime of a, is f of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. So remember, whatever's in the parentheses for f of whatever, that's what's getting plugged in for x. And so obviously in the other ones, it's just been like one thing getting plugged in, but this one's getting an a plus h, which causes things to cancel so you don't end up with a 0 on the bottom. Because as of the way it is right now, like your equation isn't going to have an h in it, but when you plug that stuff in, it does. If you do all your work correctly, the h's will cancel, so you're not left with an h on the bottom, and then you're just taking the limit at 0, which is significantly easier to solve than the one above. And obviously, again, this is provided the limit exists. Anybody's hand about to fall off? Well, there's like a page and an example left, but I don't know if we're gonna get through it all. We might stop after the next example. We'll see, and save the other thing for tomorrow. The last of it. Well, that was nice. Just gonna leave that there. I don't want to get it. I was like, what is happening? I don't even know how it fell. It's fine.
Yeah. That's weird.
All right, so an example for finding a derivative at a point. Find f prime of 4 if f of x is equal to 2x squared minus 3. Now, this is one of those problems where normally we would do it the easy way, but we're not going to do it the easy way today because, you know, we're just not there yet. Got to have a little bit of torture before you have the easy stuff.
But we can ask.
Yeah, but the AP exam's gonna have this on it next year, so you might as well get it now.
Yeah. And you have to do it the hard way.
Sometimes in multiple choice.
Was it come out with different answers?
Yeah, well, like they might just set it up for you
Oh.
and say which one's set up correctly.
Oh.
So you have to recognize it. And some parts are with a calculator and some parts are without. So lovely.
Calculators are like calculators.
I understand why they don't, because your calculator can actually find derivatives for you, so I kind of understand,
So
but
then it would just be an AP exam on whether or not you can use your calculator.
pretty much.
That's-
I thought stats got the calculator for the whole exam until I realized last year that there is a small part of it that you don't get a calculator for, because they want you to do it by hand. That's nice. Which stats is the one where I will never understand why you don't get to have it for the whole thing, but whatever. Alright, so back up. This is supposed to have a prime there. Up here. It's like blended in with my parentheses on my paper since I forgot to write it. Okay, so f prime of 4 is equal to, so we're using this definition here, the limit as h approaches 0 of, now I'm going to write out exactly like this what it would be, then we'll plug in. So f of 4 plus h, so remember this is a, which is why a up here is getting replaced with 4. So f of 4 plus h minus f of 4 over h. So now, anywhere in our equation that we see an x, we're replacing it first with 4 plus h. Well, once we've written the whole thing, then anywhere we see an x, we're replacing it with 4. So the limit as h approaches 0 of 2 times 4 plus h squared minus 3. So that takes care of this first part. Minus, I would put a parentheses because that minus goes to everything. And that's where the mistake is made a lot when it's made. So now we replace x with 4. So 2 times 4 squared minus 3. All over, it's going to still be there in calculus, h. All over does not get to go away. Are we tracking so far?
I think so.
Could you like repeat what you said for that step?
Yeah, so basically, just like when we did a function, when I just, like if I were to just tell you to find f of 4 plus h of this function, you would just plug in 4 plus h for x, or whatever is in the parentheses gets plugged in for x. And so that was this first step. So this on the top, that is replacing x with 4 plus h. Then the formula is minus f of 4, so that's why I did the parentheses, and then basically I just replace x with 4, and I have that whole piece, and then it's all over h. So now is where I get to, do the math of it all. So this is equal to the limit, and I know it gets tiring writing the limit, but you have to have it for it to be right, is equal to 2 times, now, what is this? This is a special type, not difference.
Perfect squared.
Yes, so this factors into 6, or multiplies into 16 plus 8h plus h squared.
Wait, what was this specified?
It's a perfect square trinomial.
Oh.
Now, just for the sake of saving a little bit of space here, 4 squared is 16. Times 2 would be 32. Minus 3 would be 29. Okay, so this is going to be all minus 29, would take care of that part right there. So just to save a step, to, not have to write this a million times because it does get really tedious. So then this is minus 3 minus 29, so minus 32 all over h. So now I'm going to distribute the 2 through. So the limit as h approaches 0 of 32 plus 16h plus 2h squared minus 32 over h. So 32's cancel because 32 minus 32 is 0. Now I'm left with all h terms, but just like everything else we've done, I have to factor out the h to be able to cancel it. So the limit as h approaches 0 of h times 16 plus 2h over h. Okay, we follow what happened there. Good.
Just took the
Yes.
shell.
Yes, okay. So now it cancels, so I'm left with the limit as h approaches 0 of 16 plus 2h. So if I plug in 0 for h, I'm left with 16. So your answer is 16.
That's too
I'm going to leave you in anticipation of the easy method.
That's great.
All right, we'll stop there because there's only a couple minutes left, and I'd rather just save the rest of it.
It wasn't that